Okay, welcome to the classroom. In this class, I will be teaching my mother for the first time something of Vedic Maths. Now, it has got to do with subtraction, but again, as I've mentioned already, okay, that was not cool. It is a special case, but it is going to be really handy for people like shopkeepers, but not just them, also people who are buying from shopkeepers for that matter. Now, how will it be handy? For example, you have bought some good and the total cost is 475 for that, and you hand the shopkeeper a note, a total amount of 1000 notes are not available as of now, but still. Now how do you quickly calculate how much you have to get as a change? Now you might say that okay, 475, you know the value, 700 minus 75 is 25.
525, right? 525 it should
Yeah, absolutely, but that's because you know the value.
be. Yeah.
But if I give you a difficult value, and if you are a person who is not very regular with mathematics, for example, say 471, this is slightly more difficult
Yeah,
than
not that difficult, but I can say it's four. Yeah, it's 420, 27, 8.
is
Yeah,
4
429, I
is
think.
going to be 529.
Oh, sorry, yeah, 529, right?
So yeah, so we are trying to make this work easier. And okay, I can take any complicated value, for example, 9776
No, it's
8,
difficult. I can't just
and I
calculate right
give
away.
you a sum of rupees 1 lakh. How much do I get back? So yeah, we are trying to make things simple
Yeah.
through this one. So I'll try to clear the screen for now. So the concept which is used for this, in Vedic terms we call it a sutra. That sutra, I'll say what it's called in English because even I forgot what it's called in Sanskrit. But in the test, we might have to write it in the test, so we have to memorize before the exam. It is called all from 9 and last from 10. I'll explain in a bit what's actually going on in this one. And even for the other viewers, let's just make it big, let's make it bold. This is the sutra. All from 9 and last from 10. Now, for the students of computer science and electronics, what we are actually doing with this is finding the tens complement. I'll briefly talk about that to you, although that might not be very relevant for you. So we have two types of complements. For any number of base 10. Now what is a base? When we are normally representing numbers, we know there are 10 digits from 0 to 9.
Okay.
So it is base 10. If I say base 7, it means it has only 8 digits from 0 to 7,
Why?
because that's the representation. If I represent something in base 7, for example, let me just divert a bit because it is often interesting. If I am representing something in base 7, it means we have digits from 0 to 7, that's all.
Okay.
Which means after we write 0, 1 up to 7, the next number is not going to be 8 because the digit does not exist.
You understand. So if it's base 6, that means it's from 0 to 6.
Yeah.
Something like that.
And so in this case, this the next number would be 10. And then those who study digital electronics and computer systems architecture, they would learn about how to convert between one base and another.
No, I would like to
But
understand one thing. Just wait. If the base 7, that means 0 to 7, then 8, 9 does not exist. But why 10 exists? Because it's 1.
you have to represent the value only
Mhm.
using these digits.
Okay.
So the next digit becomes 10. Okay, let me just
Like it has to be 10, something like that.
not just for that. For example, normally after 9, 10 comes. Why does 10 come in base 10? Because all the digits have been exhausted, and when you increment, you put the least digit in front and then you start from 0.
Okay.
Again, there is a system of base 16 which is called hexadecimal that has total 16 digits, 0 to 9 and A to F. So in hexadecimal, after 9 we have A, then we have B, then we have C, and it goes on like this. So for
up to
up to F,
F.
because
Okay.
we have 16 digits, 0 to 9, A to F.
Mm.
So for example, there could be a number in hexadecimal which could be written as 1AE. This is a legit number, but we would not go to that because that's not the topic of this particular lecture. Okay, let me clear the screen first. So okay, I was talking about complements. So any base will have two types of complements. For example, if you are talking about binary numbers which have only two digits, 0 and 1, they have a ones complement, they have a twos complement. A number in octal means base 8, which has digits from 0 to 7. They have a sevens complement and an eights complement. Similarly, in base 10, we have a nines complement and we have a tens complement. I'll just show you in brief how to find the complement, and you'll understand, the ones who are studying CSE and electronics, what we are doing in this thing is actually the complement, which in turn means the complement system has been derived from Vedic Maths, which was there in the ancient times. So, in order to find the nines complement, suppose I take a random number 1793. I just have to subtract each digit from 9.
Okay. Because 9 being the highest one.
Not that, because we are finding the nines complement. That's the rule.
Okay.
We subtract.
If there is a nines, like if a number can be considered which is of nines complement, then 9 number should be there. No, nothing like
No,
that.
like this is in base 10, right?
Mhm.
This is in base 10. For a number in base 10, we can have a nines complement, we can have a tens complement. So, in order to find the nines complement, again, there's a concept in computer systems architecture. If the base is represented as n, then we can have n minus 1's complement and we can have n's complement. Okay, that was bad. We can have n minus 1's complement, we can have n's complement, but these are defined terms which we have. So, following this rule, for base 10, we can have a 9's complement, we can have a 10's complement. If you want to find the 9's complement, you just subtract each digit from 9. So the complement becomes 8206. This is the 9's complement of this number. And in and now from the 9's complement,
Like complement means what? I would like to understand that first. What
I'll
do
come to
you?
that.
Okay.
I'll come to that. What a complement can exactly do. It's very interesting. Now this is the 9's complement.
That means if you like if I make 8206 plus 9, so it will be no. I mean,
No, that it
uh,
won't work exactly in that way.
okay.
You have to subtract again.
Mm,
You have to again subtract each digit from 9 to get the original number.
yeah.
So you can say that if I perform some nines complement operation on it, it gives me x complement. If I again perform the nines complement operation, it would give me x back. Because you just try to subtract each digit from 9 again, you get the same thing.
No, if, let me understand with the number only because I forgot all the algebra,
Okay.
which I did.
Okay.
It was the day and time of my school
By the
days
way,
anyway.
this thing comes from Boolean algebra, and it's also there in set theory. Like you take the complement of a complement, you get the number. So this is exactly what is happening here. Just trying to relate things with the modern context so that people find it interesting. Now this is the nines complement. If you want to find the tens complement, you just have to add one to the nines complement, and that's all. So the answer becomes this 8207. This is the tens complement of the original number 1793.
Okay.
Okay, now let's come to the rule. What does the rule say? I will take the same number for our work. It was 1793. The rule says all from 9 and last from 10. So, what we basically have to do with this thing is subtract the last digit from 10. So, we get a 7 here, and the other digits we have to subtract them from 9. So, we get
So
0.
it's 8, then 2, 0. Yeah.
So, we basically are finding the tens complement. But in Vedic maths, things were not defined in terms of numbers, they were defined in terms of verses. And that's how it has been defined there. All from 9 and last from 10. But basically,
All
they
from 9 means I have to subtract the numbers from 9 and the last number from from 10,
the
right?
last digit from 10.
Last digit from 10, yes.
So basically, they were asking us to find the tens complement. But they have presented it in this way, right?
So give some other number.
Give some other number, okay? Suppose I have anything, if I have 243. Then what is the tens complement of this using the rule which is mentioned? All from 9, last from 10. So if I do from left to right this time, this would be 9 minus 2 is 7, 9 minus 4 is 5, and 10 minus 3 gives us 7. So this is the tens complement of this thing. And the interesting property of something is that in this particular class we will only demonstrate the special case, but I'm just mentioning what exactly happens. Suppose I have to do some a minus b, and suppose b complement here represents the tens complement. This is the sign for complement, the bar.
Mm.
Suppose b complement represents the tens complement. A minus b is equal to a plus b bar. This is a property.
Haven't understood.
You will understand when we use examples, but of the special case as of this class. But this is a property. A minus b is equal to a plus b complement. And computer science students will know that a computer cannot perform subtraction. It can only perform addition. So how does a
Just a second. Let me
okay
just let me, think about it. So a minus b, and you said b complement equals to tens complement.
b complement
We can consider it as tens complement.
because it's a variable, so you can
Okay, it's b
represent it in
complement
that
is
way.
tens complement. So so a minus b has to be then a plus b complement. Okay,
Basically,
but how is it possible?
subtracting any number from another number is equivalent of adding the complement of that number to the previous number, the bigger number, or even the smaller number for that matter. And so, as I was mentioning, computers can only perform addition. So, how do they subtract numbers? They use this thing, which was mentioned in our Vedic texts long ago.
No, that is true, but what is the practical usage? Then first, I would like to know that,
Practical
because
usage, yeah, we
why
will come
should
to
I
that.
have to remember all the things?
Yeah, we will
It
come to
should
that
be very quick. I mean, the calculation process should be very quick and should be practical enough.
because we have calculators. Then why bother using this thing in the first place? I will come to that. So, in this special variation of subtraction which we were talking, we have to use exactly this rule, a variation of that. So, let's take an original example. Suppose you are at a shop and the cost which you have incurred is say 598, and you give say 2000 to the shopkeeper. How much will he give you back? Now, one thing is to subtract it manually,
Normally,
like we
the way we
normally
do
do,
it, yeah.
or using a calculator. But here we can apply that rule all from 9 and last from 10. What we have to just do is, first of all, we have this, it is the same if I add a 0 here, right? Whenever we find a 0 below here, we will reduce this number by 1. So 2 becomes 1. Now, if you apply all from 9 and last from 10 to
So
this one,
I'm telling you then. So
yeah,
it's 5, sorry, it's 4,
4,
then 0,
0,
and then 2.
and this is the answer.
Okay.
This is how much the shopkeeper has to pay you back. Simple. If I take another example here, let me take a complicated one. Suppose you pay 11,000 to someone, and the actual cost of the thing is anything, say 473. How much do you
Now I have
get
to,
back?
like, what is, I mean, should I put 0 here? Just below 1?
You can do it to make things easier for you, but it's not compulsory. We are doing it because it's the same thing, and it's easier to visualize it in this way.
That means it's 0, 0, then it should be 0. I mean, if
But
1
there's a
minus
catch here.
0,
There's a
then it
catch
should be,
here.
no?
No. Okay, go on first.
According to, but it's, I mean, if I put 0 here, I mean, I mean, the original calculation will be wrong. Okay, let's take this 473.
Yeah.
So 9 minus 4 is 5, and 9 minus 7 is 2,
2,
and 7. And what will I
7.
do after that? I mean, yeah, that I
What
have
did
to
I do
understand.
here? The first number, which is coming above the 0, reduce it by 1. This will stay as it is. And this is the answer.
Why?
Why not?
It's the rule.
No, it's actually common sense. Suppose, okay, it's a common sense. I'll tell you how it works. So you have 11,000 with you, right?
Mm.
And you subtract any number from it which is less than 1,000. What is the answer? It will be 10xxx something, isn't it?
Mm.
That's exactly what's happening.
Okay.
That's exactly what's happening. Even when we do mental calculation, that's
No,
what we
if
are doing.
now give me a number which is more than 1000, then I'll understand more.
Okay, even that's not a problem. If I just give, I'll keep this number as 11,000 here, and okay, let me say 2966, and I have to subtract.
This I can do, but what will I do with this 0 thing?
What?
It's 11,000. So then it
Okay,
should
yeah.
be 1 minus 0, it should be 1 then.
One, no.
No, it has to
1
be
minus 0.
1
1,
minus 0 here.
no,
Is
no, no. 1
1.
minus 1, because the leftmost, see, this is how it's going. This number is ending here. After that, the leftmost number which you find, you have to reduce it by 1. Wait. Okay, this is not the special case. This will require some additional things, which is not of this class. Okay,
How will I understand what the special is?
I'll tell you. This is not that particular case which we're considering. This will require some additional work here. Okay, so the special case is basically we have the number which is subtracted from another number. If you place that number above it, there are all zeros. Then it works. This particular variation. Do you get it? Like the number of digits in the number which you want to subtract. If it has an equal number of zeros to the number from which you are subtracting, as in this case, you can visualize it, then this works. If this is not the case, there's another rule.
So if it's 10,000, then the answer would be, I'm just aparting, I mean, I'm just keeping this 0 apart. It's 9 minus 2 is 7, then 9 minus 9 is 0, and then it's 1. 9 minus 6 is 1.
9 minus
And
6 is 3,
sorry, it's 3, and 10 minus 6 is 4.
4.
And what about
And the leftmost digit,
0?
reduce it by 1.
Yeah, it has to be 0 because
And now you know why you are reducing it by 1.
if the number, if you increase the number, it's 11000, then it should be 1, na?
No,
No.
no. I told you why this one is being reduced by 1. Because again, let me tell you again. You have 10,000. What is 10,000? 10,000 is the lowest 5-digit number
Yes.
in this case. 10,000 minus 1 is 9999.
Mm.
So you subtract anything from 10,000, the fifth digit becomes 0. Similarly, if you are doing 20,000 and you subtract any number from it, this digit gets
One.
reduced. This gets reduced if you are subtracting any number which is within a given threshold, because beyond that
If it's 9899, then it would
it
be.
will still work. But suppose you subtract 20,000 only or greater than that, then it's a different thing. But this is how it's working. So let's try another example as we try to wrap up the class. And how does this help? With practice, one can actually do this mentally, and they can quickly do calculations while buying something from a shop. Let's take a very huge example, maybe for this one. Let's take uh, 72.
So this is absurd actually, this example,
It's
because I will
absurd, but
not go to
okay.
the shop and I'll buy this much thing.
But okay, it's just for practice. You can consider that, right? Let's end it here itself. Let's have 9734, and you're trying to subtract. So, okay, what's the observation here? The number of digits here is equal to the number of zeros. There can be more zeros, but there should not be less zeros. So, this thing completely comes under the zero part when you arrange it.
Yes.
Now, try applying the rule.
Yeah, it's 9 minus 9 is 0. Then
Okay,
9.
let's try to do from right to left, maybe.
Okay, then is 6.
6,
Then it's 3. Sorry, 6 again.
6 again,
Then 2. Then 0.
2, 0. What happens to the digit immediately here? You got stuck because this is not the special case which we are considering. In that case, we have to take a carry, because if
Carry
you,
forward.
yeah, you have to take a carry, because when you reduce 0 by 1, you get minus 1. So there's a separate technique for that in Vedic Maths called the vinculum technique, and in standard subtraction where we do things. But for this one, let's change the thing. Let's take some any other number. Let's say this is also 3. Now what happens?
Will I put 0 before?
That's up to you. This part has exhausted. Now what do you do with the digit immediately to the left?
1, it will be 2 then in the
Yeah.
answer.
uh,
Then 2, 2,
you won't
1,
reduce these.
6.
You won't reduce
Acha, I'll
these.
read.
You'll just reduce this one.
So I'll reduce up to, then it should be 2, yeah.
This one will be as it is.
Okay.
Do you get what's happening?
Because, yeah, the number is small. The number is a huge number, and from this 9734 is a very lesser number from the main amount. So it, for 723, it should be intact, because I have to calculate from 33,000 to, if it's the case, then
It's
9734. So yeah, it's less than 10,000. Then it's 723 is common, and then 3 minus 1 is 2, because it has to be like this.
Yeah,
If I can understand.
you got it. You got it, but I think you could not frame it properly with your
Yeah, I
words.
cannot explain properly, but see, yeah.
Like, this number is less than 10. By common sense, this number is less than 10,000.
Mm.
So if you subtract anything like that, this has to be reduced by 1. Like if you subtract something in the order of 20,000 from this, then this will be reduced by 2. But we are not considering that. These are all zeros in this one. You have 30k and you subtract something, something. You get something in order of something in the category of 20,000 when you are subtracting anything which is less than 10,000 or just 10,000. That is the common sense part. But if someone wants to memorize the rule, this is the rule. You apply all from 9 and last from 10 on this part, and the digit which is immediately on the top, on the left of this number, reduce it by 1. For the rest, you just write it down
Keep
as
it
it
as it
is.
is.
Yeah.
Okay.
I'll just take final example. I'll take a small one on this one. Again, the recorder has a time limit. Otherwise, I could have explained why even this thing is happening in this final case which we are taking. Suppose I take 7,000. Let's take, and let's take 290. Now, if you try to apply all from 9 and last from 10 on this one, you might say 10 minus 0 gives us 10, but you can't write 10.
Okay.
You can't write 10 because that's not possible. So ideally what you are supposed to do is put a 0 here, take a carry forward, and
And that
do
want to be acha, okay.
things like that. That's exactly how it works if we dig deeper into this. But since if we have to just make a remedial rule, if you find a 0 on the right hand side, you just leave it as it is, and you
Okay.
start your calculation from this one.
It will be zero again.
No,
Why?
all from 9, last from 10. You are
So
just leaving it.
I'll think that this nine is the last number.
Yeah.
Then it will be one, and
The
it's eight.
7 because you're
Watch
subtracting
a
from 9.
nine. Okay, nine minus two is seven,
And
and here it should be six. I mean, I have to yeah.
reduce it
I
by
mean
1.
yeah. I mean minus one. Seven minus
Okay.
one.
So if sometime we take a very deep and longer class, after getting you to recapitulate everything of math which you have learned in your past years and get you into mathematical innovations of CIC, then we can discuss deeper what's happening and why it's happening. Like this is how I like to break down things even in class. Okay, so we will wrap up the class with this one. It's about more than 25 minutes and my recorder has not gone out yet.
Okay, no problem. Thank
So
you
yeah, thank you
for
for
whatever
anyone
I have
else.
learned first
Thank you
time.
for anyone else who have joined us in this class. And yeah, bye.